Hi, everyone. Good morning. Happy Monday. It's good to see you all. Let me switch some views around and we'll get started. Hi, good morning, everyone in the chat. Hi, Sasha, Amir, Luis, Brad, Nathan. Good morning to you all. Hi, Robin. Good morning, Owen. Owen says, good morning. Good morning, Island, Daniela. And yes, good luck to everyone. We have our fourth exam that should maybe start in the next minute or two. Um, as has been with the last few exams, take a moment to just kind of, you know, look at all the questions before you start and then just start working on it. And I promise you, if you work nonstop on the exam and the exam only, you will have enough time to finish the exam and upload and take a break. Yeah. So before we start, any general questions, comments, concerns? Owen says, is this one long? No, I think it's 5 questions. Of the 5 questions, I think 1 or 2 might be on the long side, but nothing should take you more than like 10 minutes. If it takes you more than 10 minutes, you likely aren't prepared to answer the question, and then you want to just pivot and write down as much as you know about the question and what do you have available to you to answer the question. Yeah, so just make sure you write something down. And as always, I want you all to practice academic integrity so that when you leave my classroom, you are prepared for the next class, and eventually for a career in the sciences, right? Good morning, Daniel. Okay, I don't hear any comments or questions, so I think we should start so that you have at least an extra 3 minutes. So I'll open it up right now, and the exam will be due at 11:05. Um, okay, if you refresh your Canvas screens, you can start the exam, refresh, tell me if you see the file, or if you don't, tell me that too. Okay, good. Go, go, go. Thank you, Isla. Good morning, guys. Yes, thank you, Amir. Go, go, go. Hi, everyone. For number two, the equation is split up into two lines. So just to make sure I put it in the chat as one line. That's all.
Is that a negative exponent on there? That's supposed to be good.
Yeah, and that's you can see it in the chat. Hi, everyone. About 30 minutes have passed, so you have 30 minutes left to submit your exam. Hi, everyone. You have about 15 minutes left until the submission time, and I'll remind you again when there's 5 minutes left. Hi, everyone. You have about 5 minutes left for submission, so finish up whatever you're doing and work on submitting your exam. We'll have a class at 11:30. Also, a penguin is not worth being late, so submit your exam.
Professor, did you receive my exam?
I can check, but chat with me if you can. Okay, everyone, the due date is now. So I hope you have submitted your exam. I see maybe like two or three that have not gone through yet. So just keep working on it. If you're out there working on submission, keep submitting it. Um, yeah, take your break until 11:30 and we'll be back and we'll review everything that's going to happen this week. So I'm going to stay and just finish some things in the chat, and that's all. I'll be back at 11:30. Hi, everyone. I'm coming back. I'm here. I'm here. Hi, welcome. Okay, hi, Saja. Hi, Owen. Hi, Daniela. I'm glad you guys are back here with me. Hi, Jonathan. I see your thumbs up too. Let me rearrange my screen a little bit. Hi, Nathan. Welcome back too. Um, I was trying to finish some some veggies right before I came back and I didn't finish them. It's okay. Hi, Andrea. Welcome back too. Um, okay, so let me at the very least open my slides for today and then we'll talk a little bit about this week. How are we doing? We're in the last week. We made it. If this were the fall semester, this would be December 1st. We'd have a week or so left of school and then finals coming right in. So you've made it. You've made it through the semester. There's a huge there's pros and cons, but the huge plus is that you finished a 5-unit course. The fidget spinner, Randy, it's okay. um, yeah, it's a circular object, like a thing. Anyways, we'll talk after if you'd like to talk about it. Yeah, maybe I don't know. Maybe the math isn't needed, right? Okay, so yeah, so there's lots of pros and cons about taking this class, and the big thing is that you guys have finished a 5-unit science class, a 5-unit physics that most of you need for your major, right? And Luis, I'll get to those details in a second. So that's good. Now, that's huge. It's huge that you finished it this semester. The big con or the bad thing about this is that this course is very accelerated. So as soon as this class ends on Monday, we start spring semester. So you're jumping right into it. And unfortunately, what this means for all of you and for me is that this week it's almost like we're doing double duty because you have to be ready for spring. And what I really want to remind you guys of is don't wait until Thursday to make sure you have all your classes and things. Yes, Aja, I'll see you Monday. Or Tuesday. Um, so make sure you have your courses, make sure you're emailing your instructors if you need to. I'll also say that many of your instructors are probably also teaching in the winter. So if you don't see their Canvas page just yet, hold tight. If you don't see a syllabus yet, hold tight and know that everything should be up before you start the semester. I'm working through my syllabi and my Canvas like any chance I get also, and mine aren't up yet. And from my colleagues, theirs aren't up yet either, but we're also teaching winter, so it really depends. Yes, Daniela, we're gonna sleep for 72 hours as soon as the class ends. And oh, and you're totally right. Winter pacing is really hard, and to me, it's a great time to really just go deep into the subject. And I'm a big supporter of taking these short-term classes when it's just one class. But it's really hard when we have so much else going on. So if you're working at the same time, this might not be the best time to take a class, during an accelerated schedule. So yeah, it's really fast. Oh, and Destiny has a question about 102. Yeah, I saw online that my 102 is full, including the wait list. So we will have time either tomorrow or Wednesday, probably Wednesday, but tomorrow, where I'll get all of your names and I'll make sure you have the Zoom link for the first day. And then we'll start adding everyone. But I gotta say that having a huge Physics 102 is a disservice to you. So really figure it out in the first 2 weeks what the schedule looks like for you, if it's a good time for you to take it. I'll be teaching Physics 102 in second summer session also, and Physics 101 in the first session. So if you know people out there, or if you have to retake this course or want to retake this course, summertime can be your whole physics time. Yeah. Yeah, and Luis already started class for spring. So Luis, you made the, I think you're at CSUN, right? So taking the opportunity to take classes elsewhere while you're already at the university is really great. The small con is that you have to adjust schedules. And when I was teaching part-time and I was at different systems, different institutions, I hated the schedules. One spring break was different than the other spring break, and so I never really got a spring break. And Pepperdine started like 3 weeks into January, but everywhere else was like January 3rd. So yeah. Oh yeah, and Owen, yes. When you're taking other things, it's gonna be really hard. So just huge reminder to you that spring starts on Monday. Do your best to make sure that all of the document paperwork stuff is done for Monday. So make sure you're enrolled. If you need to meet with a counselor, if you need an ed plan, if you need any help from me, let me know. I can do that. Okay, now the thing you guys are probably all waiting to hear: what is this week's schedule going to look like? Well, the first thing I'll say is this week is the same as any other week. Unfortunately, it's the same. Now, there will be some changes. The first thing is that this week we will only do chapter 13. Chapter 13 very nicely goes over so many of the topics from the entire semester. So we will get a visit of everything. Um, oh, oh, I saw a comment and that doesn't sound right, so I'll check stuff. Anyways, so we're going to do only chapter 13, gravitational motion, I think it's what it's called. And like I said, very nicely, it goes through all of the topics: angular momentum, sum of forces, um, Newton's laws. It goes over everything really nicely. So we'll be able to get through the material. It'll be very similar to last week, where everything, um, we took all of the concepts from before and brought it into angular motion. So if you felt last week was at least a little bit okay on the load, you'll feel the same way this week. Now, let me take you to our Canvas and show you the assignments for this week, and then we'll get started on the actual lecture for today. And I think we can get ahead. I really think we can. Okay. There's too much clicking I need to do right now. Let me figure this out. Okay. Okay, so let me take you to, you guys should be able to see it, motion around us. And I'll move around the modules in a second so you can see it too. So, ignore all my tabs. Also, I gotta tell you guys, like always, it's every single exam, it's so disappointing to see when your exams are uploaded. Like, it's the most disappointing thing you can see. And I've learned this year to let it go. It's not a reflection of me. It's a reflection of you, unfortunately, and what you're going through right now. But guys, like, I don't even know if this is the right answer. Like, half the answers are always wrong. So just know, your teachers know. It's not something you want to do. It's not worth the time. It's probably really stressful to cheat right now too, like really stressful. So, you don't have to do that. um, okay, so just, yeah. I was actually like, every time I search my questions, I hope I don't find them. And they're always there, unfortunately. Oh, I didn't even have the chat open. Yeah, that, yeah. Yeah, I see your comments in the chat. Yeah. Yeah. Yeah, it really sucks. Okay. Okay, so this is what our week will look like. Let me collapse everything else just so we can focus on this week. Um, Okay, so this is what a week will look like. We're going to have one set of homework. If you start reading ahead in the chapter, you can start working on it, but I don't think after today you might not be able to do it just yet. So, take a moment to look at it at least just to get familiar with it. The assignment will be due on Friday. This is not a problem set from the book, but it's very similar to the problems from the book. And so here it is. These are the problems. They're already there. They're already posted. You could start working on them. And throughout this week, we'll also go over them together. I very much challenge you to take the time to practice the questions on your own. The problem solving skills you get from doing these homeworks are what you want to take with you from this class. I don't at all expect you to remember the formulas or the equations from this class. I expect you to remember, the cool things you learned about physics, and then maybe a little bit of how to problem solve. And later that memory, that knowledge that you have will keep building. But are you going to remember all the equations? No. Are you going to, remember exactly how to use Newton's laws of motion? No, but perhaps you'll remember that, the forces on a building are balanced, right? That's how the building is standing. The reason you're not falling through your chair is because gravity's acting on you and a normal force is acting up on you too. So, um, if you read ahead, take a moment to read the questions for the homework and, try them out yourself. I'll also give you some tips and clues in how to do them. Um, Okay, I see lots of comments too. Yeah, the penguin. Yes, this is going to be our problem set for number 13. Okay, so let me keep going through and then your questions will be answered. Okay, so again, this will be due on Friday. And the one thing I got to tell you guys that unfortunately, because of our winter schedule and because I have to submit grades by the end of the 5 weeks, because many of you are depending on this Physics 101 grade to start Physics 102, I cannot accept any late assignments this week. The final time to accept any assignments for me this week will be Friday. And by the end of Friday, you will have a very good idea of what your grade is. If you get this stuff in early, you'll have a good idea of what your grade is pretty soon. So no late assignments for this week. By Saturday morning, I hope to be submitting the grades, so that you all can stay registered in Physics 102, can stay registered in statics and whatever course you need. um, okay. Yeah, so Owen, you're right. Most of the labs and stuff will be graded. So I went on a spree this weekend doing that, and I'm gonna keep doing it. Even during the exam, I was already starting. So the lab for this week is also up, and you can start doing this one right now. So this is one of the coolest videos you'll see. That when it came out last year, one of like three of my friends tagged me on it. Yeah, yeah, Mark Robert. Yeah, this stuff is great. So I'll go in detail through the video with you guys probably tomorrow, but it's posted. And this is very similar to the last three labs where you look at something around you and describe the physics in it. And what's nice is that this video will take you through the physics from the entire semester. And every few minutes, they will tell you what is the physics that's happening and then link another detailed video about that concept. So it goes from forces of gravity, Newton's laws of motion, angular momentum, friction. It's a great video, and I can't wait to show you guys more of it next week. But throughout the video, it's about 20 minutes. You'll be intrigued the entire time. You will choose a situation and show all your work, including equations, unit solutions, about the physics that's happening at any moment in the video. And again, the video will prompt like 6 different physics topics throughout the video. So you can pick one of those, or you can pick your own. And then you'll create a lab for it, just like you did for the other assignments, right? Including a drawing, labels, a force body diagram, variables, like letters for, mass, M sub S, mass for the squirrel, its velocity, position, and time. But I'll show you guys this in detail tomorrow. But I did want you to know that because of our accelerated schedule, you can start the assignment if you wanted to already, or at least read about it and plan out your time. Okay, so that's our homework. That's our lab. And now for the exam. Oh, and Daniela says he has a class that includes 3 builds of your own. Oh, that's so cool. Yeah, yeah, yeah. That's really cool. I'm gonna have to look through more of his videos. When that squirrel video came out, so many of my friends messaged me about it. So I thought, oh, this is cool. You. So yeah, watch the video. Okay, so our exam is not going to be an exam like you just took. Our exam, first of all, everyone listen, because I've gotten this question multiple times still. Um, our exam will only cover chapter 13. The exam will only cover chapter 13. Our exam will be a quiz on Canvas, an exam on Canvas, a quiz style. It is an exam, but because of the Canvas tools, it's called a quiz. So it'll be under quizzes here. The quiz will be only 5 questions, multiple choice, and you'll have one opportunity to take it. It'll be about 25 minutes long. That's it. The exam will be the quiz. Yeah, I see the cheering. Me too. I feel the same. um, the quiz will be available starting Wednesday at 12:30 after our class ends, and you will have until the end of the official exam time, which is Thursday at 12:30 to finish it. So that's a full 24 hours, but you only get one opportunity and you only get 25 minutes, and I suggest you do it from a desktop. If you do not have a desktop, make sure you're on a phone or Safari or Chrome that supports it. You can use that on the phone too, because there are pictures and stuff like that. Okay, so we will not meet on Thursday because this is an online quiz. So our last day together will be on Wednesday. Um, that's my whole spiel. Any questions? I'm sure there are questions or not, or comments, concerns. I'll miss you too, Owen. Oh, Gary brings up a great question. Will it be worth the same amount of points as the previous exams? Gary, thank you. That's the one detail I forgot. No, all the other exams are worth, let's say 100% or 10%. This one should be worth half that, so 5. So on the grading scale, everything is out of, let's say, I just scale everything to 10. So you'll see it out of 5. Okay. It's been so nice. Yes, Daniela, it has been. Luis, do we meet on Thursday? No, no, you do not need to log in. You can log in if you'd like, but you don't need to. And I'll remind you about this on Wednesday. I don't think I'll log in. Actually, no, I don't think I'll log in. Saja, so do we get our final grade on the exam right away? I think so. I think it will auto grade. And if there are any errors, I will fix that. Oh, and Keon, the conference was really interesting. Pore forming peptides are what's up. So I'm really glad you enjoyed it. I liked it too. I loved hearing the talks. It brought me back to grad school. But I also want to say that several of you had so many issues with the links, and I'm so sorry that you had that, but I'm really, really happy that you were helping each other behind the scenes on the Discord and on the group chat and things like that. Now, if we have time, I will think or try to create one more extra credit opportunity that is not additional to this, but in lieu of, for those who could not do the conference. So it will still be probably that maximum percentage, but if you weren't able to, I will try to think of another extra credit Wednesday, maybe Wednesday we'll have time for it. Yeah, I will do my best. I have something in mind that I think could work, but we got to see. you'll have enough time. But again, if you weren't able to get to it, then we'll try to have another opportunity. Oh, Luis, your name tags. Yes, I'm gonna add that as the assignment. Sorry. The name cards will be there. You should be working on it. Um, yeah, and get ready because you will have another one for that. Yeah, the name cards will be up. It's actually, oh, you can't see my screen anymore. It's hidden. It's on there, but it's hidden. Yes, and Randy says I just need the questions. I will get those questions posted today. Um, okay, so I was hoping I would start talking by 12. Are there any other comments, questions, anything else? I'm really glad you guys liked the conference for those of you that were able to attend because it was really good information. And you're right, it is difficult to understand. And it's one of those things where you have to follow like from the first word that they say very closely the whole way through. And in the end, you realize that everything is just some sort of mechanism to reach their goal, right? And science word, bio word, chemistry word, all in there. um, but eventually, you guys will be giving those talks, so it'll be really great. It'll be really great. You'll see. Um, oh yeah, I'm really sorry for those of you that had issues. They were sending several links. Like every day, I would get another email for links. Um, okay, yeah, the Pacific Standard Time. um Randy, I love Randy's comment. What I learned is that I don't know very much. You know what, that is the best position to be in, right, where you don't know anything, so that you have the space to take it all in, and you're able to just look at it all. Because imagine if you do know stuff and then you're just kind of like, when you do know, you question even more, right? So right now you're at that absorbing stage. Just absorb, and then you'll question a little bit more. Yeah, the quantum computer crystals were cool. Yeah, that stuff's really cool. My master's research was all on quantum dots, and I loved the experimental part of being able to work with quantum dots, but the theoretical part of working with quantum dots all leads to quantum computers, which is really cool. Yeah, so our lab worked very closely with the theoretical lab to get all the evidence that we needed to support our experimental data. Um, yeah, it's okay. It's okay if you guys don't know stuff yet. Um, I only knew some parts of some worlds. Yeah, yeah, it'll be okay. The other thing is that when you what did you guys think of the presentation of the presenters, like skills, their speaking skills? Because when you get to a point where you can really understand what they're saying, usually that's a really good sign of the person presenting. You want to be able to speak science as simply as possible. Yeah, they seem very knowledgeable. That's good. That's confidence, right? And you'll get there. You'll get where you will get there. And yes, Kian, number one rule of engineering 101, it taught you to be comfortable with not totally understanding everything right away. 100%. It's about the journey, and it's okay to not understand. Sit there and think about it, and then maybe ask the question or so. Yeah, yeah, they are professionals. They're experts in their fields, and I'm telling you guys, one day you'll be those experts, and um, pretty soon, like your friends and family won't even want to they won't want to listen to what you're talking about anymore. You'll have to go to conferences to have people hear you out, because the words will just become all kinds of things. Yeah, yeah. I do. I would go to conferences as a undergraduate student too, and I didn't know what the heck they were saying. But what I paid attention to when I didn't know what they were saying were how they presented, how they showed science, what I liked about their slides. Did I, try to, did the words help them? Did the pictures mean something? Could I have done it differently? So yeah, think about that stuff. Nate says my family already doesn't want to hear anything science related. Yeah. Yeah, that happens too. Don't worry, you'll get your science gang soon. We all kind of need a little group to nerd out with sometimes. Yeah. um, Ah, yes, Randy, that's a really good point. That they don't you this is what science is. You don't focus on the good or the bad. And I'm gonna sound a little bit hardcore scientist right now, but the emotions of things can sometimes get in the way of the science. And when you speak about things in facts and take out the word personal words like what do you think or I or well she wants this and he wants that, if you take out those personal terms and reframe it in terms of just the facts of what's happening, then you really start to learn things. But it's really hard to get rid of our emotions because that's who we are, right? We're humans. So um I tell you though, it makes things really simple, a little bit simpler sometimes when you can speak about things just factually, right? Yeah. Yeah, storytelling is totally key. And it goes with most jobs. Ah, yeah. Oh, and that's the right way to say it, objectively. My one of my things to do this year is to read more so that I could get better with my words because y'all know that's not my strong point. Yes, objectively. Think about things objectively. That's it. Okay, about a minute or two left, and I'm already starting my slides, but I promise we're gonna start and we'll finish before 12:30, no matter what. Um, I find it frustrating that facts are considered to be so up for debate anymore. Exactly. Exactly. Some things are just facts, and it's like everything you talk about in science should be supported with some sort of evidence. Just like when you guys answer questions on the exams, you want to always support your answer, prove that it is right and prove that it is not wrong. You come at it from both angles in a proof. Yeah, think about that. Prove that it is right and prove that everything else is wrong. It's a way to do it. I promise I'm gonna start my slides set right now. Um, I also taught astronomy at trade because my degrees were in physics, and it was the funnest class, astronomy for non-science majors, and I welcomed all the flat earthers, everyone out there that was a flat earther. I was like, come to my class, and we had that discussion. It was great. Imagine a room in trade tech with 77 students and a flat earther is just like telling us about everything, and I'm just like, tell me more, I want to know all the evidence. And there weren't a bunch, but there were like a solid five that were very enthusiastic with evidence, like some evidence that I had to think about to be able to talk about it, um yeah. So it was very yeah, it was really fun. It made for a great discussion. Yeah. Did I convert any? I don't think I did. It wasn't my mission to, but I did ask questions, right? Yeah. Oh gosh, the ice wall. Yeah. There's so much. I'm telling you. Talk with a flat earther without getting upset. Just ask them, "Oh, how does that agree with, gravity? How does that what about the edges?" I'm like, "What happened?" Yeah. I also sometimes, Nate, I feel like I can't tolerate some things either, but patience is like the thing that'll get you through life sometimes. A lot of patience. Am I showing the right screen? Because do you guys see universal gravitation? Okay, thank you, Mehmet. I shared my screen, but normally everything moves around, and this time it didn't. So I don't know. Okay, yeah, you guys all see it too. Thank you, Randy. Thank you, Brad and Amir too. Okay, so I guess the flat Earth comment is a good way to start. So we will go through chapter 13, and there's so many wild theories, and you know, oh, I just got to say it too. The other group of people I really enjoyed in my astronomy class were people who were very religious because, and I also taught at Pepperdine, so that was was supported there, and it wasn't something again that that created conflict. It was just a matter of discussion, So, um, a lot of scientists out there believe in religion, and that's okay. So imagine, instead of having the two conflict, but having them maybe support each other in some way, right? So it was really nice to see that the people who were religious in the astronomy class were starting to use science to support their beliefs, and really supporting your beliefs with some solid evidence. That's kind of cool. So yeah, there were different opinions for sure. um, so this in this chapter, we're gonna split this chapter into a small section and two bigger sections. And so today is the smaller section. So we will get through today, and yeah, we will get through to the section I want to finish at today by 12:30. And what you'll see that I mentioned already is that everything that we learned from before, we can carry it over and now say that the laws of physics apply all around our universe. In fact, the laws of physics are the thing that is common throughout our universe. So everything that we know and that have studied here on Earth, like, things falling, things changing position over time, all of that can be carried through to describe the entire universe that we see. So when you guys see this picture here, any guesses to what this is a picture of? What could it be? Or anything we know about this. Keon goes out there with the wildest theory. He says instead of a Milky Way, perhaps it's a Snicker bar. Yeah, I see lots of Milky Way. Oh, okay. Luis is a little bit more detailed and says a spiral galaxy. Yeah, this is a spiral galaxy, and it is the Milky Way. But guys, how did we take the picture of the Milky Way, of our galaxy here?
Stitched it together.
Okay. That's probably the better of the answers I've heard, Randy. That it's a stitched together picture, and then other people say, "Ah, okay." Owen says it's the iPhone 12 Pro Max. And then everyone else, Mehmet, Nathan, saying that we didn't. And Nate says maybe aliens did. Luis agrees. Oh, Daniel agreeing a little bit more, answers, supports what Randy was saying. Maybe the Hubble telescope and taking different images and stitching them together somehow, or ancient alien, or fake news. This is actually an artist version of the Milky Way galaxy, right? So we actually can't take a full picture of our galaxy in this way. Okay, or it's liberal propaganda. Yes, Owen. Yeah, we actually can't take pictures like this. So this is anytime you see one of these type of pictures, it is some sort of artist version, but it is based on some sort of theory, some sort of fact, some sort of evidence of what we know out there. For example, there are different shapes of galaxies, right? There's like the spiral one, there's the circular one, and then there's like the oddly shaped ones. That's a whole nother category. And you really want to think to yourself, how are we able to make these huge, huge measurements on a universal scale? So let's go back, guys. Come with me back to Monday, January 4th, when I showed you this picture on the first day of class. And I showed you this picture from our conversion sheet that's on the first, it's on the it's on the front page of your PDF, right? The conversion tables. And we talked about all of the different units that were on here. We even talked about light year. But if you look at everything that's on here, this is all kind of reasonable numbers that we could measure, right? We can measure a foot, we can measure a yard, a meter, a kilogram, things like this that we have no problem measuring. Or Nate says in the chat, the magnification of telescope lenses will take us really far. And optical lenses can only take us so far, that then we have to switch into some kind of like laser light system. But it does work. And then if you flip to the next page of the conversion sheet, then we get to this table that we did not see on the first day. And look at what this table has. The mass of different planets. Now, how in the world do we come up with the mass of different planets, right? Look at how large these numbers are in kilograms. In fact, this extends to even larger values from the mass of the different planets to how far they are away from the sun, right? Or to other data that we use often, the distance from the Earth to the moon, or the distance from the Earth to the sun, right? Or even the mass of the sun. And Nathan says they're all kind of approximations. Yeah, I don't know what's the significant value there, like the actual how correct we can get. And ultimately, all of these values are based on references that we make, right? References that we account for. What are those people called? There's like an institution, weights and measures. They're the ones that keep track of all of these, right? So all of this is really based on those ideas. So everything that we have starts with some approximation and some physical idea, and then we add some sort of math to it, right? Do you have a comment, Randy?
Oh no, I'm sorry.
That's okay. It's okay. Okay, so this all starts again. We can go from the small scale world, let's say a basketball, and take this to the grand universe, right? So this brings us to our first theory for this chapter, and this is Newton's law of universal gravitation. And again, this is not something that was created for the the planets. It started here, right? It starts here on Earth. And so here is the idea. Imagine that we think about the universal law of gravitation, and you think about, or the law of universal gravitation, and you think about gravity, and we constantly say that gravity is what causes things to fall down. And that's how the story goes, right? That you have Newton sitting under a tree, and some apple here decides to fall, hits his head, and where does it go? This apple decides to say no, gravity is a lie, right? What is it that instead makes the apple actually go to the ground? If the apple flew up into the air here, yeah, we'd have whole different equations. But this is what actually happens, right? The apple falls down to the earth, and then Newton thinks, what is that? It's gravity. It's something that's gravitating towards Earth. It's not actually something that's falling down. And Keon, it's actually not Earth warping over space and time. It's not falling into a void. All of that stuff, perhaps you could prove it some way or another. But what we see is that an object falls to another object. One object gravitates towards another object. And that is the beginning of the universal gravitation law. And so here's what it says. It says that one object gravitates to the other, and the direction that will create the gravitation, that will create that motion, will be due to the one that has the bigger mass. And so, of course, the Earth is much larger than an apple. So here's our first law. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So in real world, or in actual words, one moment. In actual words, these are the things that stick out here, right? Masses that are attracted towards each other. So you need two masses, right? You need one mass attracted to the other, and inversely proportional to the square of their distances. So this is 1 over r squared. So mathematically, this is what this looks like. And so here's your first equation. The force of gravity here is equal to this gravitational constant times the product of the two masses, mass 1 times mass 2, over the distance squared. Now, when you multiply this out, you multiply it times this gravitational constant. And the first thing to note is that the units here, Newton meter squared per kilogram squared, will cancel out all of the units here and leave us with newtons in the end. That's the first thing to note. The second thing that you want to note is look at how small this number is. 10 to the negative 11. So this is a constant that is going to make any number here really small. You're multiplying something times 0.00000000006, right? So this constant serves to make a number small. So if you multiply anything large here times this small number, this force is going to be really small. So now, we learned in Newton's third law of motion that there's equal and opposite, right? So if the apple is gravitating to Earth, that means the Earth is gravitating towards the apple. Now, if you multiply that times this number, you will now understand, at least mathematically, why we don't feel the force of the Earth gravitating towards the apple, because this number serves to minimize that force. And this number is literally just a constant to balance out those equations, how to make them much smaller. You're going to see this over and over and over in Physics 102. An equation that looks just like this that will describe other forces, and there will always be some constant here that is just a number to balance out the forces to physically represent what actually happens. Now, so this is that force due to gravity, and this is our big gravitational constant. This is just the scalar. We can certainly apply some some directions here. Oh, okay. Oh, Owen says, how did he get that number? Yeah, the apple said 6.67. um, you know, I don't think he got that number to begin with. I think what actually happened first was this. This f of g is proportional to m1, m2, r squared. And then somewhere in these calculations, he actually comes up with r squared because of the distance of the moon to the earth. He made a ratio between the radius, and somehow it was something like 1 over 3600. He made some ratio, and this is equal to 1 over 60 squared, right? 6 times 6 is 36 and 2 zeros. And so this is how he came up with this value r squared, because of the distance of the moon to the earth and some relationship there with the radii. Check out the crash course video. It'll show you where that number exactly came from. So after having come up with this number, there's this realization that comes in that this number is huge compared to what we actually feel. And so then there's a realization of a really small number that needs to go here. But this exact number doesn't actually come around until like the 1880s, 1900s, when we have an actual value for gravity. And gravity is known as the acceleration due to gravity. So it's not until that committee of people get together to get that value that we come up with this exact number. But I'm pretty certain that scientists knew that this was a small number to balance everything out. Okay, all of all of the actual ways he got that number, all of the ways he got that number that are in fact not true. The apple did not tell him. There was no whispering. But yeah, that's a good question. The exactness doesn't come in, but approximations come in, Owen. That's what happens. Yeah. Okay, so let us see now the direction of this. How does the direction of all this come into play now? Okay, Lord Henry Cavendish. Oh, actually, I think that might be the next slide, but I don't actually have time for it. Yeah, but check it out if you do. Yeah. This is actually a hidden slide that if we were in class, I'd go over it because it's really cool. This, yeah, spoiler alert. This experiment is really cool, and I'm sure you can find like a short video on it about how he was able to prove that relationship, the products of the masses over r squared, that does exist. But he needed this number to prove it all. And it has to do with movement of objects and being able to show that things are always gravitating towards each other, no matter what. It might not seem it, but they are. Just like on the pool table, if we walk away, the balls on the pool table are gravitating towards each other. but that force of gravity of the pool tables of the billiard balls gravitating towards each other is proportional to 10 to the negative 11, something that we can't sense or measure.
So is the theory that the light bends from this?
No, it's not that light bends, is that you're going to see you- this motion here, this motion will keep existing, and as much as this turning happens, it will cause this light to move a small measurement, and that small measurement they were then able to relate it to this. But it's not light bending. We're not able to make small measurements, right, using like a ruler, a millimeter, that are a ruler that's on the scale of 10 to the negative 11. But with mirrors and several mirrors reflecting over and over, that small measurement can get bigger and bigger. It's to the point where we can measure it. So that's what this experiment is. But you guys should take a look at it if you're really interested to where that number came from. And what this really proves is that things are gravitating towards each other, even in the absence of forces, of general forces. Okay. But if you want to see light bending, Physics 103, that's where it's at, Physics 103. Okay, so let's get to the vectors stuff. We have just a few minutes and we can totally finish this right on time. So this magnitude of the force will vary with the inverse square, right? The separation of the particles, and that's here. So we can model these particles here, and remember how we write our forces. The force of 2 exerted onto 1, the force of 1 exerted onto 2. For example, we'll see here, we'll do this one just because the order is nice. So mass 1 exerts a force onto mass 2 that is going to attract it to mass 1. So mass 1 is going to pull mass 2 towards it, and that's here. Now, when we create a direction between these could be any two particles in space. So we do not have a easy way to place an origin on here. So what we will do for this law and for Physics 102 is create something called the radial vector, which we talked about a little bit before. The radial vector is just that shortest distance from the two particles, and the shortest distance from the two particles and the direction measuring that shortest distance. So we measure the distance between the two particles with this line, and the distance from mass 1 to mass 2 is directed in the direction of this radial vector from 1 to 2. Notice it's a unit vector, so it only designates direction, that we are measuring this diagonal line. And what's really nice about this is that now we can apply an actual direction to this somewhere out in space. We have a radial unit vector. So we can apply this now to our gravitational force. So in vector form, this is what it looks like. The force that mass 1 exerts onto mass 2 is that gravitational constant times mass 1, mass 2 over r squared in the direction of the unit vector. Now notice that force that mass 1 exerts onto mass 2 is directed opposite to the direction of the radial unit vector. And that's what brings us to this negative sign here. So this negative sign belongs with the unit vector here, right? So in vector form, you will see a negative sign usually. In magnitude, you will not see that negative sign because we're only looking for that amount. What is the amount? We don't care about the direction when we consider the magnitude. So the negative sign indicates that particle 2 is attracted to particle 1. Particle 1 is exerting the force onto particle 2. So Henry, what you see here, R12 is this unit vector that tells us what direction we're measuring the distance. The distance. Can you guys hear that? The burning out? Yeah. I don't know what that is. Yeah, that's yeah. skirt. Yeah. Now I hear honking. I'm in downtown. These people should not be doing that here. Yeah. Okay, so that vector R12 is this unit vector that is only telling us the direction of measuring the distance r. So this is the direction of distance r. And the distance r is the distance between the two. Yeah, they film a lot right on that street too, right on that street. Okay, so if we were measuring, let's say, apple falling to earth, this is what the notation would look like. The force of gravity is equal to that gravitational constant and that mass of earth times the mass of the apple, right, divided by the radius of the earth squared. Now of course it's the it's the radius of the earth, right? This is the earth, and it is the radius of the earth, but you also have to add on whatever little height is there. But imagine adding in the height. Yes, I agree with Keon. Imagine adding in the height of you holding an apple 3 feet above sea level, right? 3 feet compared to the radius of the earth is insignificant. It's not going to make a huge change in the numbers. So this is a general way of calculating that, but I'll show you, I think maybe tomorrow, that if you wanted to add in a really far distance above the earth, then this would look like the radius of the earth plus whatever height, let's say the height of a satellite squared, so that it equals a total radius, right? Okay, so let us try this using a general situation to prove that things are gravitating, but at a scale that we cannot sense and we cannot measure. So here's our pool table again. You have a 0.3 kilogram billiard ball and it's placed on a table at the corners of a right triangle. We like right triangles. The sides of the triangle are lengths 0.4, 0.3, and 0.5. So this here is 0.3, all right? This is 0.3, this one is 0.4, and this one is 0.5. Anyone recognize this triangle?
Yeah.
Yeah, it's a 3, 4, 5, right? Look at them trying to help us. Okay, calculate the gravitational force vector on the cue ball designated M1. Yeah, it's a triple. It's a nice, yeah, it is. So calculate the force vector on the cue ball that results from the other two balls, as well as the magnitude and direction. So they want the total force that is exerted vector on the cue ball, mass 1. So total force exerted on 1 is going to equal the force that the other two exert onto it. So what is it? Is it 2 onto 1? I think 2 onto 1 plus the force of 3 exerted onto 1. So this is in vector form what we're doing. We're looking at what is the gravitational force of mass 2 and mass 3 acting on mass 1, right? Okay, so what's nice here is that from your image, perhaps you can see that mass 2 is along the y-axis, so it's not going to have any horizontal forces. It's going to pull straight up. And mass 3 is also on the x-axis, so it's not going to have any vertical forces, and it's going to pull mass 1 only horizontally. So that's already nice. That helps us. So let's sum these up. Okay, so we'll start by getting each one of these and then adding them up. And then we'll take the magnitude and direction. So here's the picture just for reference in case you forget. And the first one we want to add up is what is the gravitational force of mass 2 onto mass 1? Notice we write force of mass 2 onto mass 1. So you write mass 2 onto mass 1. The forces here matches the order of the product. And then the distance between them is the distance here, A. Right? The distance A. And so A squared. Now here, we don't have anything acting in the I hat direction. So if you wanted to write, plus 0 I hat, that's correct because there's nothing acting in the I hat direction. And you can just look at the image to prove that to yourself, that the straightest line from mass 1 to mass 2 is a vertical line. Okay, so let's, we can add in some numbers and calculate, right? So here's the gravitational constant. Here's the mass of mass 2, the mass of mass 1, the distance between them, and now all of these cancel out. Kilogram, 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 and we're left with newtons. And so here is the first force. 3.75 times 10 to the negative 11 J hat, which is correct in the upward direction, newtons. So while the yellow ball is sitting there, it is pulling on the white ball with us not doing anything, just standing there watching them. It is pulling on it with a force that has a magnitude of 10 to the negative 11 newtons. That is such a small number that we are never going to see it, sense it, or measure it. 10 to the negative 11. But is it happening physically in the world? Yeah. Okay, and now we can do the second one, right? The force of the third ball acting on the first one, and that's the purple one that you see here. And notice again, everything is in the I hat direction. So there's nothing acting in the vertical. So you could say plus 0 j hat if you wanted to. And so we can just plug in our numbers, the gravitational constant, the two masses, and the radius. And again, everything cancels out really nicely, kilogram, kilogram with meter squared. And so the number becomes, again, something really, really small, 10 to negative 11 newtons. So in vector math, what do? We add up the i's and we add up the j's. So this I hat plus 0 and this j hat plus 0. We're just adding them up to write it in vector form. And so here it is. The total force then that's acting on cue ball 1 is 6.67 in the I hat plus 3.75 in the j hat. And this is just the straightforward vector math that we've done. I hope that one seems okay. They helped us out by, making one in vertical and one in horizontal. That was cool. So the next question asks magnitude and direction, and y'all know how to do this. Now that we have let's say an X and a Y, we can take the magnitude and direction by taking the square root of the sum of the squares, right? So this is basically your I hat, right? Your I hat component, and this is then your J hat. Did I mix them up? No, I didn't. Okay, good. And this is your j hat component, but they just wrote the magnitude of those. So you square those, and here's your magnitude. And the last one, guys, we know how to do this. Directions. The direction is then the inverse tangent of y over x, right? And voila, there it is. Yeah. So very nicely, we can see that the gravitational force value here is so small, which is why we don't see it. But is it happening? Yes. Is the Earth being pulled up by the apple? Yeah, it actually is, but it's so small that you'll never see it. Yeah, it's so small that we'll never see it. Okay, so I have 2 minutes and I'm just gonna leave you with this last one. So is this force of gravity the same value as gravity? Some of you might be asking out there, right? Is this the same value? We can use it to solve for gravity. We can take the force due to gravity from the universal gravitation, and then we can use Newton's second law where F equals ma, and now we can solve for this value of gravity because these two F's are equal to each other, right? A force equals a force. Fg is equal to F. So if we equate these two equations, we can then solve for the value of gravity. So this is F is equal to F sub g. And now we can eliminate the small masses, right? This is as if the force, Newton's second law of an apple falling, right? If the apple is falling, we draw the free body diagram and the only thing acting on it is the weight, F equals mg. So the masses cancel out, we solve for this g, and you see now that this is the value of g. If you put in, everyone, the gravitational constant, the mass of Earth from that second slide that I showed you, and the radius of Earth here, with no extra altitude, right? No extra altitude, you will get the value 9.8. If instead you start to add some height, meaning let's say you go up to the Leaning Tower of Pisa, the Eiffel Tower, some really high mountain, Mount Everest, right? Or you're a satellite and you now have some additional height, the further up you go, the lower your value of gravity will be. And this is why we say back from chapter 5 that the further away you are from Earth, the less effect that gravity has on you. And the same thing for the moon, right? The moon has such a small mass that this number of mass is going to be lower, which is going to result in a lower gravity here. Um, yeah, that's it. Any comments, questions, concerns? How are we doing out there? All right. Thanks, Sanja. We got a thumbs up. Okay. Yeah, so I totally get it if we're a little tired and yeah, we'll get a little better. Let's see. So when I got skiing at when I went skiing at Big Bear this weekend, oh my God, is that me? Is that you guys? Stop writing on my screen. It's one of you. Stop writing on my screen. Um, okay, so I think Randy says when I got
Go.
yeah, go ahead.
It's go. Not got.
Oh, okay. So when I go skiing at Big Bear this weekend, I will have a lesser gravity. You know, I don't know how high it is, but you can calculate that, Randy, and it's true. And you guys have seen this physics professor at MIT. He's much older. He's super cool. Does the best. Yes, it does the best things. He has one experiment that shows measuring people's height when they from them standing and then sitting down and standing back up. When they stand back up, sometimes the force of gravity is still acting on you, and you can be just like a little bit shorter until you like really stand up. So yeah. Daniel, it is true that the moon causes waves. That's another reason. um, yeah. All of this is connected, guys. You're totally right, and I'm glad you're seeing it because all of it is connected. It's all physics that we learned from the Leaning Tower of Pisa, where Galileo said, "Hey, all these masses accelerate at the same rate." You know. Okay, so I'm gonna stay after, and I have other questions in the chat to me, so I'm gonna stay after and help anyone with whatever they need. Um, I'll see you guys tomorrow for class. Please do come. We're not done yet. So yeah. Oh man, I wanted to see snow this weekend too. Anyways, I'm gonna stop recording. I'm gonna stay. If you guys have any comments or questions, please feel free to stay. Get some rest. Go move a little and then get some rest. Y'all need it. Bye everyone. See you
Thank
tomorrow.
you, Professor.
Bye, Keon. I'll see you guys tomorrow. I'm going to stay. Let me just